Welcome to qnawire.
In this problem, let's see here, we got another, not an ideal, a reheat ranking cycle, but not ideal. And so in this case, we have a high pressure side up here at 10 megapascals. Low pressure side we're given this time of 10 kilopascals. We're actually told what the power output is, and that's 80 megawatts. The temperature at, let's see here, I think I wrote that wrong again. T3 and T5, not T4. So up here, we are at 500 degrees Celsius. The pressure here is a 1 megapascal. We're given that. The efficiency of the turbine is now 80%, and that of the pump is 95%. So at 3, we can get the enthalpy and the entropy at 3 because we know the pressure and temperature. So the entropy at 4 prime, straight down here, is the same as entropy at 3. So we can get the isentropic enthalpy at 4. And from that, from these two things, and the turbine efficiency, we can find the enthalpy at 4, the actual enthalpy. Now at 5, we have pressure and temperature, so we can get enthalpy and entropy. And then we know for the isentropic case, the entropy at 6 is the same as the entropy at 5. So that would give us a quality factor in the isentropic case of 94.9%. And then the enthalpy in the isentropic case would be 2,461 kilojoules per kilogram. Now, we can then use this and our efficiency to get the actual enthalpy at 6. And that is 2,665 kilojoules per kilogram. Now, it turns out that I drew this wrong. And that is actually a saturated vapor. So let's actually adjust my picture here. I'm going to just adjust the vapor boundary here. And so we're going to put that come down into there. And so then we'll do a little bit of this comes up and it meets with this. So there's 6 now. That's 0.6. So we're a little bit superheated there. Now let's see here. We have so then we can get the temperature because we know we have the enthalpy and the pressure, and so the temperature there is 88 degrees Celsius. Now we know the pressure, and we know it's a saturated liquid here, roughly. So we can get the enthalpy. We know the specific volume then. And so again, we can get the work, their specific work to get the, and again, using the efficiency, we can get the pump, the specific work that we need to put into the pump, which then gives us the specific enthalpy at 2, which is this plus this. Now we have the enthalpy at all of our points. So the heat transfer in, enthalpy here minus enthalpy here, plus enthalpy here minus enthalpy here. The work in the turbine, we can figure out by looking at the enthalpy here minus the enthalpy here, plus the enthalpy here minus the, I think I said that wrong. The enthalpy, the enthalpy here minus here, plus the enthalpy here minus here. So that would be the output work of the turbine, which is about 2,300 kilojoules per kilogram. So the net work of this whole system, we take this and subtract the work from the pump, which was this, and we get about 1,280 kilojoules per kilogram. Again, this is always very small compared to this, so sometimes you can just even neglect that. It will, make your efficiency a tad bit artificially high, but anyway, we can take this and divide it by this, and we get an efficiency of 34.1%. And then they also want the mass flow rate. So we know the power that the actual power, net power that we're putting out is 80 megawatts. So we can divide it by the specific net work, and that winds up giving us 62.7 kilograms per second of flow through this system.